Now want to see how do we modify these experiments we have already seen so that we can work out sorbitol product constants of any other compound that we can be given. Let me look at how to determine sorbitol product constant of silver ethane dioate. So I want sorbitol product constant of silver ethane dioate. I'm just going to change this to silver ethane dioate. And then you'll see it, you will see the procedure simply flowing. So wherever I have magnesium hydroxide, I'm going to put there silver ethane dioate. The titration here is going to change. So it's a matter of modifying this experiment to make it fit into my treatment of results. So I remove this magnesium hydroxide. I remove this. I remove this. I remove this. And maybe the whole of this. My duster is so slow that it will clean everything here. So how do I determine sorbitol product constant of silver ethane dioate by direct titration? This is silver ethane dioate. Silver has valence of 1, the ethane dioate iron has valence of 1. I will say excess solid silver oxalate or silver ethane dioate is added to a given volume of distilled water in a container. The mixture is shaken for some time and left set at a given temperature to attain equilibrium. Mixture is then filtered to obtain a saturated solution of silver oxalate as filtrate. Okay. Silver ethane dioate as filtrate. Now what do we do next? A known volume of the filtrate is pipeted into a conical flask. Here the change we are going to say, we shall say the solution is acidified and warmed. But now I want you to understand this main concept here. Whenever we are titrating an oxalate with the permanganate, the oxalate must be acidified first and then warmed. Am I clear, Muhammad?
Yes, teacher.
Forget that whatever you do after that experiment is wrong. So a known volume of the filtrate is pipeted into a conical flask, acidify it and warm it. I'm repeating, a known volume of the pre-filtrate, which is an oxalate solution, is acidified and warmed, and then titrated with a standard solution of potassium permanganate. And titrated with a standard solution of potassium permanganate. Then you write the equation for this reaction. Okay? What is that equation? You'll take your time to see whether you can derive it and balance it. I'll write a balanced equation here. 2 potassium permanganate plus 5 oxalate plus the 16 hydrogen ion is here. Will give me 2 manganese 2 ions plus 10 carbon dioxide gas plus 8 water. That's the equation. You write it and get a mark for it. So you use this equation and stoichiometry of that equation to get the molar concentration of ethane dioate ions or oxalate ions using the equation above. Okay. So taking the molar concentration of ethane dioate ions as X moles per liter, what shall we do? We shall have silver ethane dioate giving us 2 silver ions plus oxalate ions. So using molar ratio, you go through all those ones, we shall have that our concentration of silver ethane dioate will be which value? Remember, during this titration, we are titrating a standard solution of permanganate with oxalate ions. So by calculation, we shall get moles of permanganate used. Use this molar ratio 2 to 5, get moles of oxalate ions in the given volume that we pipeted. Those moles which we shall have got will be in this volume of the filtrate. Work backwards to get the moles in 1000. That is the molar concentration of the oxalate ions, which you have got as X. Then using molar ratio, what do you think will be the value of concentration of silver oxalate according to this equation? Will it be a half? No, it won't be a half. According to the equation, it will be equal to the molar concentration of the oxalate ions. Not so. The molar ratio here is 1 to 1. Okay?
Yes, teacher.
So it will be, the concentration of oxalate ions will be X moles per liter. Then the concentration of the silver ions, according to the molar ratio here, when you look at this, the concentration of silver ions, if this is X, then this one will be twice that value. That okay, Muhammad?
Yes, teacher.
Yeah, according to the molar ratio here. Or you can use the molar ratio of silver oxalate to silver ions. If this is X, which you have got here, then this will be twice X. Such that now our KSP is equal to the concentration of silver ions squared, concentration of oxalate ions, which will equal to, the concentration of silver ions is 2X, but it is squared. The concentration of the oxalate is X. So you have your answer as 4X cubed moles cubed DM negative 9. Remember, this would be moles per liter, but all of it is cubed. So that's where you get that answer there. This method can work for any oxalate. It can be calcium oxalate, where I will modify this to form calcium, and the value for the expression of KSP also changes here. That is by direct titration of silver oxalate. However, if I want to use conductivity measurements, still I would simply modify this. This is so interesting. I'll simply modify this experiment here. I'll simply modify this experiment here. I'll simply modify this experiment here. And then I'll get my final answer, as we are going to see. So what shall I do if I want to solve a product of silver ethane dioate or silver oxalate by conductivity measurements? If I want the sorbitol product constant of silver ethane dioate by conductivity measurements, this is what I will do. I'll get excess solid silver oxalate and dissolve it in a given volume of distilled water in a container. Shake the mixture for some time, allow it to set at a given temperature to attain equilibrium. Filter the mixture to obtain a saturated solution of silver oxalate as filtrate. Electric conductivity of the saturated solution, K solution, per ohm per centimeter is measured using a conductivity meter. The electric conductivity of water at the same temperature is read from the books. Go on. Molar conductivity of silver ions and oxalate ions are read from the tables. How do you treat your results? The electric conductivity of silver oxalate is given as the electric conductivity of the solution minus electric conductivity of the water. Molar conductivity of silver oxalate at infinite dilution is equal to molar conductivity of silver ions twice. I'm multiplying this now by 2 because of this. You get the difference now here. Plus molar conductivity of oxalate ions. So here the 2 is now here, not on the hydroxide ion as we saw previously, because we have 2 silver ions here and 1 oxalate ions. So we shall also take an assumption that molar conductivity at infinite dilution of silver ethane dioate is equal to molar conductivity at any given concentration of silver ethane dioate. This since the solution is so dilute. So molar conductivity of silver ethane dioate is always equal to 1000 K silver ethane dioate over C, where C is solubility in moles per liter. The moment you do that, you end with this same treatment as we have seen here. You do this same treatment as we have seen here. But instead of the C, the X here, we shall now have C, because it's what represented solubility. Are we together?
Yes, teacher.
Lastly, I want us to see how to determine solubility product constant of an iodate. How do you get that of an iodate? Using conductivity measurements. And in this case, the iodate I'm going to use, I may use copper 2 iodate. By direct titration. I'm going to get that of potassium iodate by direct titration. So the procedure is the same. We want now copper 2 iodate. Copper 2 iodate. Procedure is the same. Copper 2 iodate. Pipeted and titrated with the, this is where now things begin to change. With a standard solution, the previous experiment didn't require us to use an indicator because potassium permanganate acts as an own indicator. So here we're going to titrate the saturated solution of copper 2 iodate with, before titration, I want you to know the theory here. We have iodate ions. The iodate ions, from them we want to acidify them, react them with iodide ions so that we liberate iodine and water. We liberate iodine and water. Then this iodine liberated is reacted with thiosulfate. So before titration, we have to treat the iodate solution by adding potassium iodide and then acidifying it. So we need an extra change here. Pipetted into a conical flask. After pipetting it into a conical flask, and a known volume of potassium iodide is added. Why do we add potassium iodide? That's how we treat iodates. A known volume of potassium iodide solution is added. We're adding the known volume of potassium iodide solution to introduce iodide ions. And also a known volume of sulfuric acid is added. Why do we add sulfuric acid? To introduce the hydrogen ions or to acidify. So the moment that those three are combined, iodine will be liberated instantaneously, such that what do we have? We have iodate ions in the solution. In the presence of the hydrogen ions, these are usually 6. I'm not deriving these equations because of time. Take time to see whether you can derive them from half equations and balance them. Plus the 5 iodide ions here, it gives us 3 iodine plus 3 water. That's the equation for the reaction that occurs there. Now this resultant solution contains iodine. So the resultant solution containing iodine is titrated. We titrate now the whole resultant solution here with a standard solution. This is a bit longer, of sodium thiosulfate. In iodometric titration, we use starch indicator. Using starch indicator. This is a good experiment that can even be set practically. All these experiments we have done here can be set practically. So what happens there now? We have the iodine being titrated with thiosulfate. Ions give us iodide ions plus tetrathionate ions. All these tetrathionate ions. So there is a 2 here. Now from this, we determine the molar concentration of iodate 5 ions. We work backwards. Okay? So the molar concentration of iodate 5 ions is determined using the 2 equations above. How is that done? You remember this is the standard solution. So I will begin from calculate the moles of thiosulfate that reacted, use molar ratio, get moles of iodine liberated. Those moles of iodine liberated are from here. So you can combine the 2 equations and get moles of iodate that reacted to liberate these moles of iodine. Those moles of iodate ions are in the given volume of the result of the solution we titrated. Then get molar concentration of iodate ions. And maybe take it to be X moles per liter. We now come to the treatment of results. Now come to the treatment results. How will our treatment be for the results here? We have copper 2 iodate. Copper has valence 2, iodate has valence 1, plus aqueous. This gives us copper 2 ions plus twice iodate ions. So now we have already got the concentration of iodate ions from the titration experiment there as XC moles per liter. What will be the molar concentration of copper 2 ions? Muhammad, what will be the molar concentration of copper 2 ions according to this molar ratio here?
A half X.
It will be a half X. Very good. Moles per liter. Now we can get your KSP directly. KSP is equal to molar concentration of copper 2 ions multiplied by molar concentration of iodate ions, which is equal to a half X. This is squared by them. A half X into XC squared. That is a half X into X squared. What does this give me? Give me a half XC. Is it a half X cubed? Yeah, it gives me a half X here. This is X squared with the X cubed, and then moles cubed, dm power -9. That will be the sorbite product constant. That will be the sorbite product constant of copper iodate by that titration experiment. I hope you can use your free time to do the same measurements using conductivity measurements and get that experiment described. I hope this is fair enough. Take your free time and see how to use to explain the same experiment, but using conductivity measurements as already described in our previous experiments. These videos will be posted on YouTube. Subscribe to our channel for more and invite friends. This is the only topic I'll share completely on YouTube. I may not share all the other topics completely.